Welcome and thank you for attending our presentation. Today's talk is about Tailslide, an open source feature flag framework designed for easier code deployment with automated failure protection. My name is Steven. I'm here with my colleagues Trent, Jordan, and Elaine. We're a group of remote developers who've been working on Tailslide for the past couple months. For today's talk, we'll first introduce the problem domain that Tailslide focuses on, then describe what feature flags are and how Tailslide fits into its competitive landscape, followed by explanation of Tailslide architecture and demonstration of its feature flag and circuit breaking capabilities. Engineering decisions we made, future work for Tailslide. Finally, we'll end the presentation with Q&A. So at a high level, Tailslide is a feature flag solution that untangles code deployment and feature release. Deployment is one of the last steps in a software release cycle. It is the process of moving code from development environment to the production environment. On the other hand, feature release is the action that makes new or changed functionalities available to the user. Here, a feature is something that satisfies the needs of customers. It can be an addition of functionalities, improvement in performance, or availability for application. Historically, feature release was often tied with deployment, since code in applications is active by default. This means once code is deployed, all users receive the new feature. The downside of traditional deployment is that when features break, developers must scramble to their feet and deploy hot fixes on top of the problematic deployments or roll back the problematic deployments altogether. This leads to unpredictable repair wait time or extended service downtime. This tight coupling nature between deployment and feature release means that once code is in production, developers have little control as to whether features should be active or not. Tailslide provides a server-side feature flag solution that enables developers to safely deploy on demand, instantly toggle features on or off at runtime, test code in production environment with so-called dark launches, control the release of features to selected users, monitor features performance, and automatically shut off poor performing features with recovery options. For the next couple minutes, a hypothetical startup, Healthbar, will be used to illustrate how feature flags can simplify deployment and feature release for microservice-oriented companies. Healthbar is a startup that provides platform as a service related to information technology for hospital, medical, and healthcare companies. Deployment at Healthbar is often a major event because it impacts its entire user. Due to the serious nature of patient data, avoiding service downtime is crucial for its clients. This means that before any code can enter production, it must go through rigorous automated tests, rounds of approvals among stakeholders, and this typically takes Healthbar over a month to deploy new code into production, which is slow by industry standard. Recently, management has asked development teams to implement more features to expand Healthbar's customer base. However, due to low deployment frequency, each deployment at Healthbar involves many new features, which makes developers anxious before deployment due date. The developers would like to be able to gradually introduce the new features to their clients so that they can gauge the performance and reliability of the new features before affecting all of their users. The developers found out that they can achieve gradual rollout of their new features with Canary deployment. Canary deployment requires setting up a separate infrastructure that holds the new features alongside the existing infrastructure. A load balancer is then placed before the two infrastructure to control user traffic to either version. This allows developers to initially trickle users to the new version and gradually dial up user flow toward it over time. If the new infrastructure encounters an issue, the users are redirected back to the original version, thus minimizing potential service outage. With Canary deployment, the teams are able to increase their deployment frequency and quickly deliver those features for customers. Upon seeing the team's success and how the new features have matured enough, the management wants to integrate those new features into Healthbar's core business offerings to stay competitive. Developers were confident deploying new features with Canary deployment because the new features were isolated. They had little worry about interactions or conflicts among the features. But integrating those new features into existing services poses new challenges. Integration of features introduces dependency of features among teams. In addition, individual features may work in production alone, but may have conflicts when run together. Developers also want to test different combinations of features for the overall integration. For instance, a potential solution may involve any combinations of features A, B, and C. Ultimately, testing the synergy of those features in production environment is the only way to ensure they function correctly under real-world conditions, such as high traffic load, infrastructure problems, and unaccounted client use cases. To experiment with the possible combinations requires multiple deployment and infrastructure for hosting those deployments, which increases deployment cost and complexity. With Healthbar's limited resources, the developers need another deployment strategy to integrate those features with single deployment. They found feature flags. At its simplest, feature flags embed conditional logic into applications that allows developers to dynamically control the on or off state of features at runtime. Fundamentally, feature flags allow developers to decouple deployment from feature release, such that deployment is now only about moving code into production, and feature release solely depends on runtime logic. With feature flags, developers can dynamically toggle features on or off in production, as well as release features to selected users. Learning from their deployment experience, the developers determined that the ability to monitor the performance of new features and automatically turn off the problematic features will be very helpful in reducing service downtime. It prevents requests from hitting services that are down and provides those services recovery periods with limited traffic. It also gives developers peace of mind. For instance, if they release new features on Friday, they don't have to manually check or respond to whether the new features are functioning normally on the weekend. The teams decide on using feature flags for its ability to test different combinations of features in production with a single deployment. The ease of toggling features on or off without requiring expertise, and the ability to reliably and responsively handle fallback strategies that developers specify. While researching for feature flags as a deployment and feature release strategy, the developers find various existing solutions that range from full enterprise solution with observability and automatic circuit breaking to open source feature flag frameworks. LaunchDarkly is the most prominent enterprise solutions, and it offers an easy to set up and feature rich platform with circuit breaking that Healthbar wants. However, it comes with high service costs and requires sensitive patient information to be stored on the cloud. Both are not an option for Healthbar. Furthermore, since it is not open source, the developers may not be able to configure it exactly the way they want at a later time. For open source frameworks such as Unleash, they typically offer either self-hosting of their frameworks or using their cloud services. They offer many features just like LaunchDarkly, but are harder to set up and don't come with circuit breaking. Finally, they found Tailslide, an open source framework that is fully self-hosted and easy to set up. Healthbar only needs to pay for infrastructure costs. Well, it only comes with essential feature flag options. It does include the circuit breaking that developers need. Since Tailslide satisfies most, if not all, of their requirements, the developers at Healthbar agree that it is their best option. Next, Jordan will walk through Tailslide architecture with demonstration.
Thanks, Stephen. Hi, I'm Jordan. Welcome to our project Tailslide. This is a diagram of Tailslide's overall architecture. Tailslide consists of 4 main pieces. The first of these is a full stack application called the Tower. It handles the management of feature flag rule set data and stores circuit breaking configuration information. The second key piece of our system is the NATS Jetstream, a message streaming system that facilitates communication between the other Tailslide components. The third key part of Tailslide are the software development kits that are embedded in each individual user microservice. These SDKs incorporate into the microservices the code that is required to react to flag state and circuit status. The final part of our project is the Aerobat. This application handles keeping track of success and failure rates generated via our SDKs and determining when circuits need to be tripped. Now that we've gone over the overall architecture of Tailslide, we're going to take a look at the deployment process. Tailslide is a self-hosted, open source feature flag framework. Since Tailslide is not a managed solution, all data, such as flag rule set data and user application information, is stored on the user's own infrastructure and is not shared with any external parties. Tailslide provides a simple out-of-the-box deployment strategy, which will spin up all components of Tailslide on a single server using Docker. Depending on a user's needs, Tailslide also offers individual components as separate repositories on GitHub. These can each be hosted on individual machines or with any hosting service. This provides the flexibility to scale and use different components as needed. To deploy Tailslide with Docker, a user needs to first clone the Docker branch from GitHub, then ensure the appropriate configuration files are present, and finally pass in an SDK key argument along with the Docker compose up command. Now we're going to focus in on just the feature flag functionality in detail. Later on in the presentation, Trent will cover the circuit breaking side of the functionality. There are 3 components core to the feature flag architecture: the Tower application, the NATS Jetstream, and the software development kits. One thing to note is that the blue components are Tailslide specific. They're intended to support the user-provided microservices highlighted in orange. The software development kits, shown in blue with the flags, are a library intended to be incorporated in a user's microservice. Now we're going to zoom into the Tower portion of Tailslide. This is a full stack application that handles the functionality related to feature flag management. It consists of a React front-end user interface that allows users to do things such as create an app in a flag, make edits to flags, toggle a flag on and off, and view logs related to those flags. All of the feature flag data is stored on a Postgres database, and whenever a change is made to the flag data, the backend Express server publishes the full set of new flag-related information onto the NATS Jetstream, where it is then dispersed to the rest of the project. Before we take a more detailed look at the other components, the NATS Jetstream and the SDKs, I'm going to show some examples of how to use the front-end interface. If a user would like to create a new app, they will want to navigate into the dashboard. This brings the user to a page that shows all apps available in the project. As you can see in the example, Healthbar already has 3. In order to add an app, the user will just need to provide an app name. Once the app has been created, we can see it populated in the app screen as shown in the demonstration. If the user would like to add a flag to an app, they can click into that app. This brings up a screen showing all of the feature flags related to that particular app. To add one, we can bring up the Add and Edit flag modal. The user can then enter a name and a description of the new flag. There are several other features that can be managed via this modal, but for now, we're just going to create this new flag. To toggle a flag on or off, a user can simply click the toggle button to the right of the feature flag in question. If the user would like to see logs related to a specific flag, they can navigate into that flag from the main flag screen. That will bring up the flag information screen. From there, they can select the second Logs tab at the top. This will bring up the history of log information related to that particular flag. If a user would like to see logs related to all flags, they can use the Logs button on the left menu to see all logs related to every flag in every app on their deployment of Tailslide. Now we're going to move on to another main component of the Tailslide architecture. That is the NATS Jetstream. This is a third-party asynchronous message streaming service. It's a key piece of Tailslide because we envision this system as being able to accommodate many different user microservices. As the number of microservices plugged into Tailslide increases, so does the traffic between those microservices and the feature flag information stored in the tower. We need NATS as a way to decouple the microservices from the tower application to keep Tailslide very scalable. Another benefit of using NATS is that it allows for real-time communication. This means that if a user were to make a change, such as toggling a flag on or off via the front end, there would be no delay in that logic being available to the microservices for use in rendering feature flags. Also, NATS offers guaranteed message delivery. This means that if for some reason the Tailslide tower were to go down, or if a user's microservice went offline and needed to be spun back up after the latest feature flag data has been published to the Jetstream, there's no issue at all. The NATS Jetstream always stores a record of the last full set of feature flag data. So when a microservice is brought online for the first time or back online, it will immediately have access to the latest information. Whenever there's an update to the feature flag data, the tower publishes the full set of flag logic to the NATS Jetstream. The Tailslide software development kit embedded in each user microservice contains a NATS consumer that is listening for updated flag data. Once the consumer receives a new set of rules, the SDK will store that information and can use the logic immediately when evaluating whether or not a new feature will be displayed. Going back to Stephen's discussion of how useful it is for engineers to be able to deploy many new features at once and use the functionality of each independently, the ability of this system to support events such as the user toggling a flag on or off from the front end without requiring a redeployment for application behavior to change in response is a crucial benefit of Tailslide and feature flags as a whole. The final feature flag related component of the Tailslide architecture is a software development kit embedded into each user microservice. This SDK is responsible for consuming the most recently pubbed flag data from the NATS Jetstream, storing that information, and using it for flag evaluation at runtime. Currently, Tailslide provides SDKs designed to be used in server-side applications. To use the SDK, a user will need to first install the SDK and provide a configuration object that includes an SDK key, an app ID, which is a number representing the application the user's microservice belongs to, and a NATS server URL to connect into the Jetstream. Each flag in a microservice will require its own instantiation of the toggler. This toggler will be used to evaluate whether the new or existing code will be run. The code on the right here shows an example of a configuration object and the instantiation of a new toggler. The if-else conditional statement at the bottom of the code represents the heart of Tailslide's flag toggling logic. We'll get into how this works a little more over the next couple of slides. But first, I want to talk about two key drivers for whether a flag gets toggled on or off. The first is rollout percentage. This is a number that represents the percentage of end users that a developer intends for the new feature to be enabled for. The second term is whitelisted users. These are users that are intended to always be shown the new feature. These could be developers or other people on the product team who need to test the feature out. Within the Tailslide Tower database, whitelisted users are kept track of as a comma-separated string of UUIDs. As you can see from these images, the Tailslide user interface allows developers to update whitelisted users and change the rollout percentage for any flag as they see fit. That if-else statement that I pointed out earlier as the heart of whether or not a new feature is called uses the isFlagActive function pictured here. This function first checks if a particular flag is set to active. If the flag is set to inactive, the flag will evaluate to false and fall back to the pre-existing code within the else statement. If the flag is set to active, the function will then check if the user making a request to the microservice has a UUID that is whitelisted. If their UUID is a match for any of the UUIDs stored in that particular flag's information is whitelisted, the flag will evaluate to true. This means that the new feature code in the if part of the statement will be evaluated. If the flag is set to active and the requester is not whitelisted, the function will make the final determination based on the rollout percentage. This involves hashing the UUID to a number between 1 and 100. If that hash number turns out to be greater than the rollout percentage, the flag will evaluate to false. If the hash number turns out to be less than or equal to the rollout percentage, the flag will evaluate to true. And now Trent is going to explain Tailslide's circuit breaking functionality.
Thanks so much, Jordan. Let's now take a look at the second portion of Tailslide's architecture, circuit breaking. Calls to a new feature over a network introduces an additional point of failure. Whether the new feature itself fails or the connection between service degrades, this can lead to a poor end user experience or further outages within an application. Tailslide has implemented the circuit breaker stability pattern to protect against these failures. Tailslide has taken a unique approach to implementing this pattern within its architecture in order to serve the deployment of new features as well as integration with its feature flag management system. The circuit breaking architecture integrates with feature flags by observing the health of connections to new services and automatically closing off these connections when failure occurs. Connections to services can then be reestablished through an automated recovery process. Tailslide circuit breaking implementation can be broken down into 4 stages. First is the monitoring and emission of success and failure data related to the new feature deployed behind a feature flag. Second is the storage of this data in a Redis time series cache. Next is the evaluation of error rate and circuit state handled by a Tailslide application named AeroBab. Lastly is the propagation of any change in circuit state back to tower via NATS jetstream, which is then published back out to all SDKs, completing a full cycle of messaging within Tailslide. The first stage of circuit breaking is the emission of success and failure data. This takes place within the microservices themselves by monitoring the success of calls to a new feature using the Tailslide SDK. Jordan has already covered the import and configuration of the Tailslide SDK, as well as instantiating a new toggler object for a flag. Once instantiated, the object not only exposes the flag evaluation method, but also an emit success and emit failure method called directly on the object. These methods are configured to emit a success or failure data point by writing directly to a Redis time series cache and should signal a successful or failed operation as related to the new feature. As opposed to a traditional circuit breaker function wrapper, these methods are exposed in order to allow the developer to explicitly call as they see fit, based on their own success or failure conditions. Redis time series is a time series module built on top of a Redis cache. The Tailslide SDK for each slide microservice is configured to connect directly to the cache for writing via the emit methods. Each write contains the flag ID, the success or failure status, as well as the app ID as metadata. Each data point written to the cache is stored under a key defined by flag ID and the status of the operation. Each key holds all data points associated with its flag. Thanks to the time series data structure of the cache, a timestamp is added to each data point, correlating with the time at which the success or failure took place. This is an important aspect of Tailslide's circuit breaking capabilities and allows for querying aggregate data within a specified time range. This is the key to evaluating real-time error rates and also enables Tailslide to provide graph visualizations of circuit health. Tailslide is also built to handle scaled microservice applications and thus evaluate circuits in aggregate. All instances of a new feature deployed via a feature flag, even if scaled horizontally many times, are stored and analyzed as a single circuit, ensuring a consistent application state for the entire user base. The next stage in Tailslide's circuit breaking architecture is handled by AeroBat. AeroBat is a lightweight node application responsible for querying Redis and evaluating the current error rate of flags. AeroBat fetches data by pulling Redis at a configurable interval, querying for some success and failure counts emitted by application microservices. Each poll queries for some success and failure counts over a developer-defined window of time. This window effectively acts as a sliding window, constantly checking the summed values starting at the time of the query. This ensures that any sudden spikes in data are smoothed over and gives a more accurate view of the current error rate. All flag data is efficiently fetched in a single query through the use of an app ID metadata tag. AeroBat is responsible for parsing this data for each flag before evaluation. With these summed values, AeroBat is able to calculate the current error rate for each flag within a specified window in real time. Each pull of Redis updates these values, allowing AeroBat to constantly monitor the health of deployed features and connections to them. In order to evaluate circuits, AeroBat must be aware of the developer configurations set for each flag. AeroBat receives these circuit rule sets by subscribing to NAT's Jetstream, consuming updated rule sets as they are published by Tower anytime an update is made. This lets AeroBat know what flags are active, the developer set error threshold, and any automated recovery configurations. AeroBat stores these rules internally for evaluation, updating its state anytime a new rule set is received. Each time Redis is pulled and error rate is calculated, AeroBat will then evaluate the error rate against the error threshold to determine if the circuit should be tripped open. If the error rate surpasses the error threshold, the circuit is tripped open. At this point, AeroBat must then publish a message to NAT to notify Tower of this change in circuit state. Tower is then responsible for updating the circuit state by toggling the appropriate flag off and propagating this change to the SDK instances via NAT, effectively cutting off all traffic directed to the new feature while the circuit is in an open state. The circuit will remain in an open state until a developer toggles the flag back on or the circuit is automatically recovered. While Tailslide's default behavior of tripping open a circuit protects against the failing feature, it still requires an engineer to respond to the failure in order to turn the flag back on and close the circuit. This time to recovery can increase if an engineer is unavailable, especially during weekends or nights, leading to additional downtime for a feature and a degraded user experience. Tailslide has implemented an automated recovery system that follows the principles of a circuit breaker half-open state, which Tailslide refers to as in recovery. The display shown here is a view of the Tailslide dashboard, showing the circuit monitoring view available for each flag. This display gives developers a real-time visualization of the health of the circuit. At the top is a graph displaying error rate against error threshold, with an additional view of request counts over time. This graph is updated in real time by pulling the Redis cache for current data over the selected window. Below that is a live view of all circuit recovery configurations, including the current state, as well as the current health of the circuit itself. Through the use of NAT's WebSocket integration, this display also updates in real time, giving developers a powerful yet concise view of the circuit. Walking through the stages of recovery, the display to the right will first show a circuit exceeding its error threshold and entering an open state. When initially tripped open, a recovery delay period will begin, during which the circuit will remain open and the flag will continue evaluating faults, preventing any traffic to the new feature, and hopefully allowing time for the feature or connection to recover. After this delay period, the circuit will enter into recovery. While in recovery, the circuit will reclose, turning the flag back on, but only directing a reduced portion of users to the new feature, determined by the initial recovery percentage. During this recovery period, AeroBat will continue to monitor the error rate of the circuit, and if the threshold is surpassed, reopen the circuit and start the recovery process again. AeroBat will incrementally increase the percentage of users directed to the new feature, configured via the recovery rate and recovery increment percentage. The circuit health display shows the current percentage being directed to the feature. If the health is able to reach 100%, AeroBat will send a message that the circuit has recovered and the circuit will return to a fully closed state, directing the full rollout percentage of users to the feature. Although the circuit monitoring dashboard page allows real-time monitoring, it's also important developers can be aware of changes in circuit state when not actively monitoring, whether to reduce mean time to recovery or to debug a circuit that continues to trip open. Tailslide allows developers to configure Slack channel alerts for any changes in the circuit state. This configuration is as simple as entering the webhook URL into the flag setup card. Tailslide will then send a webhook request with details of the flag and its updated state anytime there is a change, giving developers a peace of mind knowing they will be immediately alerted of any circuit changes. I'll now pass it off to Elaine, who will discuss some of the engineering and trade-off decisions made while developing and building Tailslide.
Thanks, Trent. I'm Elaine, and I'll first walk us through the various engineering trade-offs we made as we built Tailslide. One of the major decisions we had to make was around communication. How were we going to deliver flag information to the SDKs and to Aerobat? Our solution needed the following features. It needed to be able to support a publish-subscribe messaging pattern, which is an asynchronous service-to-service communication pattern. In this messaging pattern, publishers publish messages to a subject and fan out those messages to subscribers in real time. In our case, upon any change to the flag rule set, our server would need to publish the updated flag rule set to a subject, where it would then be fanned out to all subscribers, which would be the user microservices. This ensures that all user microservices receive the latest flag rule set. It also needed to be fault tolerant, meaning it could provide guaranteed delivery. Due to the fact that networks and distributed systems are inherently unreliable, if a user microservice went down or became unavailable due to a temporary network partition, our solution would still need some mechanism to guarantee delivery to the service once it was up again. It also needed some way to persist sent messages and provide message replay of the last sent message. Message replay is a feature of some message brokers, which allows them to resend messages to new or existing subscribers, regardless of when those messages were first received by the message broker. By having message replay, when a new user microservice comes online, they can immediately be pushed the last sent message, representing the latest flag rule set. Also needed to be able to authenticate both publishers and subscribers, securing the flag rule set data and ensuring that only applications that should have access to the flag rule set get that access. And lastly, it needed to be easily deployable and relatively lightweight. With these requirements in mind, we considered different alternatives. For one, we considered utilizing our server to directly serve flags to the user microservices via service sent events. This solution is easy to deploy as the server is already part of our existing infrastructure. However, the solution would be entirely DIY and would result in us having to engineer all of the desired features from scratch, which although provides us with maximum customizability, would be a complex task. Another key issue with the solution is that it suffers from a lack of separation of concerns, as our server would now need to service requests from endpoints, communicate with the database, and also be responsible for sending updated flag rule set to every instance of a user microservice. We also considered various message brokers, such as RabbitMQ, which is a lightweight open source message broker, but unfortunately, it did not support message replay. We looked into Kafka as well, and although it has all the capabilities we required, it is quite a complex and feature-rich tool and is primarily meant to be used for very high volume throughput event-driven architectures. Due to the fact that we don't anticipate flag rule set data being changed on a very frequent basis, we opted not to pursue usage of Kafka. Finally, we landed on Natch Jetstream, which is an open source message broker that met all of our requirements, including supporting pub/sub communication, being fault tolerant and guaranteeing delivery, providing message replay and authentication, and being a lightweight and easy to deploy message broker. Other decisions, however, needed to be made, particularly around how we were going to architect our circuit breaking functionality. Our proposed solution needed to implement the following. It needed to emit telemetry data. Specifically, the data needed to differentiate between a feature flag that is operating as expected or failing. Once emitted, we would need an appropriate data store in order to hold that data. Lastly, we would need to query that data store at a periodic interval in order to assess the current error threshold and compare that to the configured error threshold as defined by the user in order to assess if a circuit was tripped. If so, we would then need a way to communicate that information to propagate that change across all user microservices. With these high-level problems in mind, I'll now discuss the different alternatives we considered. When it came to emitting success and failure data, we had different proposals here, including emitting observability telemetry data or emitting based on user-defined success and failure events. Emitting observability telemetry data consists of enriched data that includes things such as logs and metrics. Although enriched, this data could require additional infrastructure, For instance, a telemetry collector could be needed in order to receive, process, and export the data. Ultimately, this solution came with increased complexity, and because we were looking for a lightweight and simple solution, we opted not to pursue this. The other option we considered was to give users the ability to specify the conditions of a failure or a success directly in their code, using the emission methods defined in our SDK. This approach differs from traditional circuit breakers, which can be more rigid in their evaluation criteria. These are often implemented by wrapping HTTP requests between synchronous service-to-service communication and predefining success and failure criteria based on response status codes. Our approach, which allows the users to decide for themselves what their specific success and failure criteria would be, gives flexibility to the user and is also simple to use. The second decision we had to make was around the storage of this data and what data store would be suitable. Our data store would have to support a high volume write throughput because every user microservice would be writing to the data store when it encountered the emission methods. The data store would also need to support reads that would occur on a periodic basis. This happens when Aerobat queries the data store to assess if a circuit has tripped. And lastly, the data we were storing was ephemeral in nature and was very simple. It would just consist of an identifier for the flag, a timestamp that indicated when the write occurred, and if it was a failure or success event. To leverage our existing infrastructure, one option we considered was having the SDKs published directly to a success or failure message log topic within Nets. We would then query that message log topic periodically. Although feasible, consistent time-bucketed querying of persisted messages in a message broker is a more complex and involved process and is not natively supported by Nets and would require custom code. Due to the time series-like nature of our data, we also considered using a feature-rich time series database such as InfluxDB. If we had decided to pursue a full-fledged observability approach with rich telemetry data, the complexity of our data increases and could benefit from the additional features provided by a time series database. However, due to the simplicity of our data and our specific use case, as we didn't require these robust features, we chose not to pursue this. Instead, we ended up using an implementation of Redis that added a time series data structure to Redis. Redis is an open source, lightweight, in-memory data store, which was simple to deploy, simple to use, and allowed for high volume throughput and performant read and write capabilities. Using Redis time series allowed us to easily group the time series data into buckets for assessment by Aerobat, and allowed us to set a time to live on that data, so stale data could be cleared out periodically. An important feature due to the fact that high volume of data needed to be ingested. Time-bucketed data could then be sent to the front end for graphing and visualization purposes. Lastly, a third decision we had to make was around how we wanted to communicate to the server if the error threshold exceeded the configured threshold. One option would involve setting up an API endpoint on the server and having Aerobat communicate directly with the server using HTTP requests sent over the network. Although feasible, this approach is not fault tolerant and could be susceptible to drop messages if there was a network partition. Instead, to improve reliability and guarantee message delivery, we opted to have Aerobat published to Nets, and we configured the server to consume for Nets for the appropriate circuit breaking subjects. Overall, our circuit breaking architecture resulted in success and failure emissions being flexibly designed by the user, telemetry data being stored in a Redis time series data store, and when circuits were tripped or recovered, messaging being sent via Nets to notify the server of changes. That concludes our engineering trade-off discussion, and I'd now like to take you through some future work we have in store. Future work we are considering includes having user accounts authenticate before being granted access to the front-end UI. In addition, we would like to build out the ability to see the detailed flag change history, such as who toggled the flag on or off, or who edited the circuit breaking options for a flag. We're also looking towards adding SDKs in additional languages to support our users. Currently, the client library SDKs we support include Python, Golang, JavaScript, and Ruby. In the future, we would like to add additional popular backend languages such as C# and Java. And lastly, we would like to add the ability for users to circuit break based on other trigger criteria, such as user-defined HTTP response codes and user-configured response time thresholds, specifically when the circuit breaker is used for synchronous service-to-service communication. That concludes our presentation. I'd like to thank everyone for coming, and I'd like to open up the floor to any questions anyone might have.
All right, I can read the question. I'm curious to hear more about what you did to explore Kafka and at what point you decided not to pursue it further.
Okay, so I can take this question. Thanks for the question, Miles. We considered Kafka early on in our architecture as we thought through what pieces we'd like to use in order to construct our feature flag functionality. Ultimately, we decided not to pursue it further just due to the types of use cases you would normally see Kafka used in. It's normally meant for very high volume throughput event-driven scenarios where you're streaming thousands of requests a second. And for our specific use case, since we see flag rule set data being toggled on or off on not as frequent of a basis, we opted not to pursue usage of Kafka just to avoid the complexity of that tool. If anybody in the group would like to add on, feel free.
Okay, second question. Which pieces were the most interesting to work on?
I guess I can answer from a personal standpoint here, just because I specifically covered a lot of the circuit breaking. I'm sure everybody kind of found different portions most interesting, but I thought it was really fun to kind of figure out how to integrate that within kind of this future deployment we're going over and the future flags system. It kind of offered up a lot of interesting challenges just because it's a fairly established stability pattern. It's been around for a while. It's been implemented by some pretty big names, but each implementation kind of works differently, whether it's at the single process level, whether it's looking at an application more holistically. And the integrations we've kind of seen with feature flag systems out there were pretty specific to very large enterprise solutions. A lot of integrations handling, these applications that maybe had a very big full stack observability tool already entered. So kind of our problem space of approaching this from a smaller company that kind of wanted this functionality built into future deployment just offered up so many kind of different challenges, that Elaine kind of went over. And it was just a lot of fun kind of deciding how we were going to implement that and kind of just finding all the little trade-offs on the way. And sorry, I see the next. Yeah, go ahead.
No, I was just going to say, I was going to throw in my own. I thought it was pretty interesting to learn a little more about like NATs and just like the idea of how microservices communicate with one another as a whole and kind of like thinking through that problem. I don't know if Elaine, Stephen, do you guys want to answer your favorite too?
Yeah, I can add on top of what Brand and Jordan have mentioned. I think personally it was really rewarding when we took the time in the beginning to plan out our architecture for how all the pieces communicate with each other. And it was very satisfying that because we took the extra time to make sure that the communications between the components are solid. When we implemented all those components, it was really amazing to see how all the pieces fall together. Anything you want to add, Elaine?
Not too much. I feel as if most of my teammates covered most of the interesting things. I also found it really rewarding just to be able to work in a team environment with other engineers, including some group and pair programming. It's just really nice to see how other people approach a problem and how we can talk about things whenever we come across issues or discussions that we'd like to have. I'm just going to move on to Missy's question. And she'd like to know exactly how does a user currently specify what constitutes success or failure for a particular feature?
Yeah, so I can answer that one. That was kind of covered with the concept of that emit success and emit failure method that's exposed in the SDK. And we did that very intentionally to give some flexibility to the developer. Because if you take a look at a lot of the traditional circuit breaking libraries, what they'll do is they'll have you pass in an async request function to a constructor, and they'll return an object that wraps that function. And internally within their SDK, they'll monitor essentially the response coming back from that request. And then they're usually going to be taking a look at the exact status code. So then they'll have some sort of like pretty strict definition of what success or failure. So they'll say, you know, anything in a 200 range is a success, anything outside of that is a failure. And we felt that that was a little bit constricting, especially in the sense of, you know, leaving it up to how the developer might want to deploy this new feature through various means. So we decided to expose those methods directly in the sense that they could simply just call the emit success, say within a try catch block, or if they wanted to kind of build it in any way, they could then kind of define those conditions that they thought determined whether it was a success or a failure, which could be, you know, maybe checking that code, and maybe you're open to some other status codes not throwing an error. So we kind of just did that for giving the developer a little more flexibility and control over the implementation. While I'm at it, I guess I'll just read the next question, which is, can you talk a little bit more about the incorporation of Redis, and at what point in the design process was that considered and integrated?
I can take Audrey's question. So originally we had 3 different ideas of how we want to store that success or failure information. One solution, as mentioned in the presentation, was using Net's JetStream to store those information, and then we can grab the information from the Net's JetStream and using our own logic to calculate the error rate for, say, the past 10 minutes. But we found out that Redis had this time series data structure implementation that we can utilize. Since we're only interested in aggregate error rate for a period of time, we can use Redis time series to make a simple query to get that error rate information we need. After considering the trade-off, we decided that using Redis time series was much simpler implementation. Also, we were originally considering storing other observability information like logs or metrics. But for the minimal implementation, we decided not to store those information. So we disregarded the option of having a full open telemetry observability option there. So yeah, that's how we ended up with the Redis time series approach.
Yeah, and I'll quickly add on to that. It had some other kind of very powerful properties that ended up making it the best option, including that you can essentially set like a full time to live on your entire time series cache. So we could set that at about an hour, and all of our data would be expired on a rolling basis, making it super, super lightweight. And then it also has very kind of like powerful query language for time series, even allowing us to create kind of buckets within, say, a time window range. So we kind of receive a data response with, say, a 10-second window. We could bucket within that each second, and then receive the sum value of each second, which was really useful for doing some visualization on the front end.
Okay, next question. Did the entirety of your collaboration occur remotely? And yes, it did. Next question. Trent mentioned observing other solutions that offer circuit breaking logic. Are there any recognized standards, protocols, or best practices that you were able to follow? Or was it mostly taking leads from existing solutions?
Did a good amount of research into this. A lot of the kind of like the base references you'll see kind of with any looking into circuit breaking is an older Martin Fowler article where he then references a book by Michael Nygaard called Release It, where he kind of discusses a lot of stability patterns related to distributed applications. So that's kind of where the whole concept was, I guess, first laid out within this context. As far as implementation, Netflix's circuit breaker was like a big one that's now been deprecated. And now there's like some kind of major language specific libraries out there. So we kind of took a look at that. Most of them are quite configurable because realistically, application to application, you're going to have kind of different needs in terms of what you kind of define as a condition for breaking open a circuit, as well as that kind of concept of half open recovery. So that's why we tried to really allow a pretty granular amount of control over that recovery and that circuit breaking process. But generally speaking, as far as standards, it's usually based on error rate when looking at requests to a service, based on an error threshold that's been surpassed. There are some libraries out there that handle it based on maybe like a timeout condition, but there weren't really, a ton of best practices in the sense that it's very specific to the actual implementation and the application.
I would like to add that circuit breaking logic is taken from electrical and engineering concept. I guess the logic itself is just a fundamental circuit breaking pattern there. But what makes it interesting is depends on the architecture of your microservices or applications. The interactions among those moving parts can vary greatly. Yeah, that's an interesting part of implementation of the circuit breaking logic.
All right. I think at this point, if there are no more questions, we will conclude our presentation. We'd like to thank everyone for attending and for your questions and for your attention throughout our presentation. And thanks so much. Enjoy your Wednesday, everyone. Bye.